All right, so we are going to do this little foldable to help us graph rational functions. So you have a test tomorrow. This stuff, I mean, technically, radii is not on your test, but everything except the t squared is stuff we've already done, and that material is on your test. So this is just kind of putting it all together and adding one little tiny new thing. And then the assignment that goes, because we'll graph a little bit today before the end. The assignment that goes with today, you don't have to graph, you're just finding the stuff we're talking about, which again would also help you on the test because that's what I'm testing you over before we actually start graphing, okay? So this is, the little acronym is PPD radii, right? So under this PPD part here, we are going to just write out that acronym for radii. So it is RAT squared EY. Now, some people call it radii, some people call it rattouille. I'll be honest with you, when people said rattouille, I was like, I don't get it. All I could think of was the ratatouille. I could see this mouse, and I don't know how does that have anything to do with this? Until somebody pointed out something real obvious, which most of you probably already catch, and I couldn't figure out for the life of me. It's rat2e. That totally makes sense, but I've called it radii for so long that it's just radii. It doesn't matter how you say it as long as you know what is all in it, and it's all good, okay? All right, so the PPD part of this, what do these stand for? All right, so the first thing when we look for before we try to graph a rational, let's see if I can straighten this up, ooh, is when you have a function, you want to look to see, does it have a parent? Is there a parent function that goes along with it? The two parent functions that we did look like this. We had this one, which is our reciprocal function, which was f of x equals 1 over x. And then we had this one, which is our reciprocal squared, which was f of x equals 1 over x squared. Now, we did a lesson on it because you need to be introduced to them. You need to know that they exist in the parent functions and how the transformations work and all that stuff. But I did not put it on the review, and I didn't put it on the test because my experience has been if we do too much stuff with those parent functions, you want to make all rational functions have parent functions, and they don't. The great majority of the rationals that we are going to graph don't have a parent function, and none of that stuff with transformations works or makes any sense. So even though I chose to leave this on here and not rename it just PD radii, we'll talk about it, but then even when it's very clear there is a parent function, we're not going to graph it that way. We're going to graph it the same way we graph all rationals, which actually makes it easier anyway, and it'll be consistent. But if you flat out know it, or if you were asked to use transformations, then you can just do transformations that you already understand. But don't try and do transformations on things you think have a parent function when it really doesn't. And I think that part is what's confusing for some people. It's like you're not sure when it does and when it doesn't. So we're just going to pretend like they all don't, and then we'll be able to graph them all just fine. Okay. But then the PD part, we found PD multiple times in the last week or so. What do you think that stands for? Very good. Point discontinuity. That is where the holes in your graph are, right? If you have them. You don't always have a hole in the graph, but if you did. And to find that, that means we have factor or factors, because you could have more than one hole, containing x that is common to the numerator and denominator. It comes first in our little acronym because it's always should be the first thing that you do after finding domain, if you have to do domain. Because everything else is done with the reduced function. So if you can reduce it, you reduce it, and then you move on. Okay, we good on that? All righty. So then we have R, which stands for roots. All right. And what's another word for roots? Zeros. Okay. So I guess radii or rattouille was better than zattouille or zadie because it really doesn't matter what we call them there. But our roots are the x-intercepts should not be brand new information, right? X-intercepts, which are the zeros of the numerator. And that has to be found after reducing. Everything else we do is found after reducing, if you can reduce, because they don't all reduce. Okay. All right, we good with that? And we know how to do that. You've been doing that for a long, long time. All right, the A stands for asymptotes. Specifically here, the vertical ones, because we refer to the horizontal and slant asymptotes as something else. But when you're just talking the asymptotes, we're talking the vertical ones. Okay, and we've been finding those together for a while too, which weren't brand new anyway. So if we have vertical asymptotes, that means we have a unique factor containing x in the denominator. And the reason it has to say unique factor is because if it's not unique to the denominator, that means I can cancel it out. That would make the whole. That is not what where my asymptote comes from. And so, and when we have these, remember these are lines, and we always write them as equations of lines. They are lines determined by the zeros of the denominator. So zeros of the denominator give us the vertical asymptotes. Zeros of the numerator give us the roots or the zeros of the function itself. Okay, we all good so far? All right. So then the t squared. So this is the part where it's semi-new. And the t, this stands for two things. And both of the things also start with t. This says, do any factors of r or a, so the roots or the asymptotes, do any factors at all, numerator or denominator, do they have an even exponent? Now, when we were sketching our polynomials, if we had a factor that had an even exponent, what happened when on our polynomial sketch there? It was tangent. Very good. We had a bounce, so that meant it was tangent to the axis. Do y'all remember that? So if I have this factor here that has an even exponent in the numerator, it works the same way as it did for polynomials, and that gives us tangency. That's just a different form of the word tangent, tangency. So this is what the graph would look like, just part of the graph, obviously not the whole thing. Tangent, that's just the same bounce as it was before, tangent to the x-axis. If I have a factor in the denominator with an even exponent, that gives me what we call togetherness. So tangency and togetherness are those two t's. And we're going to draw three little x and y axes here to put our little examples. And then on each one of these, we're going to have a vertical asymptote, just so I can show you some examples here of what togetherness means. This is an example of togetherness, and so is this, where on either side of the asymptote, the function is going in the same direction. If they go in opposite directions like this, that is not an example of togetherness. Okay. Tangency from the numerator, togetherness, if you always say them together, tangency and togetherness, you've got numerator over denominator, maybe keep up with which is which. Any questions about that? Okie dokie. Then E, we're on the E here. E stands for end behavior. End behavior. We have as the very first way we looked at end behavior, we said as x approaches infinity, f of x approaches something, right? That's what our end behavior is. What's happening way out at the infinities that maybe we can't see? Okay. I'm sorry, what? It depends. It's going to approach whatever our asymptotes are. Yeah, so it depends, but it could definitely approach 0. And here's how we figure this out. We could have a horizontal asymptote, which we abbreviate as HA. And so we look at our function, we decide if it's top heavy, bottom heavy, or tied in degree. If it's top heavy, we don't have a horizontal asymptote. If it's bottom heavy, then our asymptote is at y equals 0. Those two O's in bottom give you that 0, all right? And then in that case, then it would be a yes there. All right, and then, 1 second. Okay. If it's tied in degree, then y equals the ratio of the leading coefficients of the numerator and denominator. Make sense? We talked about it this week. Okay. Then slant asymptote, if the degree of the numerator is 1 more than the denominator. Because remember, if it's top heavy, I don't have a horizontal asymptote. That opens the door for me to possibly have a slant asymptote. If it's 1 more than I do, I figure it out by dividing and then I ignore the remainder. These are the two that we're really going to deal with. This right here is just going to be another little kind of FYI. Like what happens if it's more than 1 greater? So this says if the degree of the numerator is more than 1 higher than the denominator, then it has what we call polynomial end behavior. So if you remember when I showed you the asymptotes the other day, I showed you the slant and the vertical and horizontal, and then I showed you one at the end, and I said this asymptote's actually a parabola. We're not going to do any of these, but I want you to know that there's other things. When you get past it being a slant asymptote, then the rest of the asymptotes are what are called curvilinear asymptotes because they're not straight lines. And so if it is higher by an even number, then the polynomial end behavior I'm referring to is what we knew how our ends looked before. If we had an even degree, then the ends were the same, right? It was either up, up, or down, down. So higher by an even number, the ends are the same. Higher by an odd number, then they are opposite. So if I had an x to the 5th function over an x to the 2nd function, then it would the numerator would be 3 higher. So then that means that I would have actually a cubic asymptote, which means that my ends would be opposite. So again, this is just kind of an FYI. It's good for you to know that there's other things out there, but these are the ones that we're going to work with strictly. Okay, so then the last one here is the y. This stands for the y-intercept. And you've been finding y-intercepts for a very long time as well. And we do this the exact same way you have on all of them. You substitute 0 in for x and solve for y. It's the same as finding f of 0, right? And because it says y-intercept, it is written as an ordered pair. Okay. Any questions about this little handy-dandy foldable here? All right, so this is your PPD ready. Keep it handy. I'm going to hand you another piece of paper so we can do a little bit of graphing using this stuff and show you how simple that is. You can go ahead and fold this in half. We don't cut it or do anything fancy with it. It's just set up for an ISN, even though we don't have one. Here's this before I forget. Okie dokie. So I'm going to fold this in half here. And I know that your grids, the lines are very hard to see. They did not copy well. If you look really closely, you can kind of see dots where kind of the corners of some of the boxes. I will use a different copy machine for the rest of them. I did not realize that happened until it was way too late. So just do the best you can to get it in about the right spot. Mine, I just printed off so I could have white, so that's why you can actually read mine. Okay, so when I give you stuff that we're going to graph on paper, I have the PD righty written out over here. If you have to graph in Delta Math or some other place, it may not all be written out, but you got to find it all to be able to graph. And so that's why understanding what the acronym is is very, very helpful to you. So we start off, we've got to figure out first if we have any point discontinuity. So in order to do that, I have to factor. So I'm going to factor this, and I get x plus 2 over x minus 3 times x plus 2. Am I going to have point discontinuity? Yes. What is the x value for that? Negative 2. Okay, so then I cancel that out. My reduced function is 1 over x minus 3. This is what I use for all of the rest of it. That technically is a reciprocal function with just a shift, but we're not going to look at it like that. We're just going to treat it like we would every single rational, and it actually makes it easier. All right, so then I've got to figure out what the y value for this is. So I take that negative 2, I substitute it into my reduced function. So basically I'm finding f of negative 2. It's going to be 1 over negative 2 minus 3. So that's negative 1/5. So that's the coordinates of the hole in my graph. Roots come from the zeros in the numerator. Do I have any? No, but I don't write none. I do this because this, well, mine looks like junk, so sorry, it just didn't get that done right. But what I'm trying to do, let's try again here. There you go, that's a little bit better. What is that thing called? The empty set, yes. So I'm going to write the words again. You don't write the words and do it, and you wouldn't just write the words. This is just like a little reminder if that's what that is, and then that's the last time I'll write it. Do I have any vertical asymptotes? Yes, those are the zeros of the denominator, and it's an equation of a line, so it's just at x equals 3. Tangency and togetherness would mean that my factors would have to have exponents, and they don't, so this is none. Is this top heavy, bottom heavy, or tied in degree? Bottom heavy. So I have a horizontal asymptote at y equals what? 0. Very good. So if I have horizontal, I can't have slant. So it's and you don't have to have one or the other, but you definitely can't have both. Y-intercept, that means I find f of 0, 1 over negative 3. So my y-intercept is just 0, negative 1/3. Then I need to do my sign chart. I'm going to rewrite my function down here so you can see it, because I know you can see it on your paper, but when I have to shift them out, I can't see it. All right, so on my number line, I put all of my zeros and all of my asymptotes. I don't have any zeros. So I have an asymptote at 3, and asymptotes always get open circles. So then in this function, if I choose 0, that makes it negative overall. If I choose 4, that makes it positive overall. This is a very simple sign chart. So this is negative, this is positive. So now that I have found everything I'm supposed to find, I'm going to go graph. The first thing I want to put on my graph are my asymptotes. So I have a horizontal asymptote at y equals 0. Put that one in. And I have a vertical asymptote at x equals 3. Do your best to find 3. Just at least label it on the axis if it really doesn't look like it's at 3 for you. Then I'm going to go down the line and graph the points that I may have. So I have a hole at negative 2, negative 1/5. So negative 2, negative 1/5 is about right there. So I'm going to put the hole right there. I don't have any x-intercepts because there's an asymptote there, but I do have a y-intercept of 0, negative 1/3. So it's about right there. So those are the only 2 points that I have on my graph, but I'm expected to actually graph this. So what my sign chart says is that from negative infinity to 3, my graph is negative the entire time. So from negative infinity to 3, it's negative all down here. And I know how asymptotes work. This has got to hug this asymptote right here, and it's not going to cross over it because it never comes positive. And then this has got to come down here and hug this asymptote. So there's really only one thing that could happen here, and it would look a little bit like this. Be careful not to draw straight through the hole that you drew, because then it's no longer a hole because you just filled it in. Now, from 3 to infinity, my sign chart tells me that my function is positive the whole time. I don't have any togetherness, so I know it's got to hug the asymptote up here, stay positive, so it'll look something like this, but I can't just throw that in there. I got to have at least 1 point. So sometimes we have to choose some points. I'm just going to choose 4 and see what happens. I'm going to find f of 4 using my reduced function here. That's just going to give me 1. So when x is 4, y is 1, since I know the general shape of it, I feel like that's enough points, and I can sketch this in. Remember, everything's curvy, nothing's pointy. It looks like that. Okay. What questions do you have? Anything? Alrighty, then let's try the next one. So I'm going to start off the same way by factoring. This is going to give me x minus 2 times x plus 1 over x minus 2. Am I going to have any point discontinuity? Yes. These cancel out. My x value is at 2 for the whole. My reduced function is x plus 1. So this is what I use for everything else. I substitute the 2 into here, and I get 3 for my y value. What are my roots or my zeros? -1. So it's a set, but only has one number in it. It's -1. I don't have any vertical asymptotes because I don't even have a denominator, so that's none. And there's no exponents, so there can't be any tangency or togetherness. This is clearly top-heavy because, again, there isn't a denominator, so I cannot have a horizontal asymptote. Technically, it's its own slant asymptote. But again, I don't want to get too far out there in theory land, so we're just going to go with none. Then what's your y-intercept? 1, 0, 1. Very good. So then once again, I'm going to rewrite this so it's down here. So the only thing I have on my number line is a 0, which is at -1. It's a closed circle. If I substitute in a -2, that's negative overall. Substitute in 0, that's positive overall. So it's another super simple number line that we really wouldn't even have to graph this, but we're going to do it on all of them because we're absolutely going to need them on some. So then I go to graph this. The first thing I want to graph for my asymptotes, I don't have any, so there's nothing to graph. So the whole is at 2, 3. So I plot that. What is this an equation of? It's just a line, right? So at least I know that. That's a good thing. My root, I have an x-intercept at -1, and I have a y-intercept at 1. Since I know it's a line, I don't have to graph any other points. Like everything that was in what I had to find is good enough. I'm just going to line it up. And then, again, don't draw right through the hole that you made. And this is how you get a line with a hole in it. What questions you got? We good? Awesome. Let's look at the last one. So I'm going to have to factor. This gives me x plus 4 times x minus 3 over x minus 3 times x plus 2. Now, just FYI, not every single graph that you have is going to have a hole in it, but these 3 happen to. So I can cancel this out. That makes my x value a positive 3. My reduced function is x plus 4 over x plus 2. And this is what I use for everything else. The y value, I take the 3, substitute it in here. That'll give me 7 over 5, so that's just 7 over 5. What are my roots? -4, good. It's just the 0 of the numerator. Do I have any vertical asymptotes? X equals -2, because that comes from the denominator, right? There's no exponents anywhere, so no chance of tangency or togetherness for this one. Is this top heavy, bottom heavy, or tied in degree? Tied. So my horizontal asymptote is at y equals what? 1, because it's the ratio of the leading coefficients. And then since I have a horizontal, I can't have a slant. My y-intercept is at 0, what? 2. I'm going to rewrite it. F of x was x plus 4 over x plus 2. All right, my number line. I got 2 things that go on there. I have a -4 and a -2. The -4 is a 0. The -2 is open because it is an asymptote. If I substitute into here, I'm going to choose -5. -5 in both of these, that would give me negative over negative, which is positive overall. Between -4 and -2, I'd use -3. That would give me positive over negative. That's negative overall. And 0 would give me positive over positive. That's positive overall. So this is what my number line looks like. Okay, so then we go to graph. Okay, I have all this information. I'm going to put it all on my graph. The first thing I want to do are my asymptotes. So I have a vertical one at x equals -2 and a horizontal one at y equals 1. So then I have a hole. It's at 3 7/5, so that's like 1 2/5. So I'm going to go to 3, a little bit over 1, a little less than 1.5, about right there. You got to make an open circle anyway. There's no way to get it super accurate. You're fine. I have an x-intercept at -4, so I put that point on there. I have a y-intercept at 0, 2. Oh, that's 3. Dang it. I'll have to let it dry before I can erase it. I can't count. There we go. All right, so now I have this, and if I use my sign chart over here, I know from -infinity to -4, my function's positive. So starting out here at -infinity and going to -4 right here, it's positive, and it's going to have to hug the asymptote, so it's coming right here. Once it hits -4, it's 0. Then from -4 to -2, it's negative, so it's going to follow the asymptote down like that. So that makes total sense from my sign chart, and I get that. Then from -2 to infinity, it is positive the whole time. So again, I don't have any togetherness, so I'd have to start up here. The only thing that makes sense is to sketch this in like this. What we don't know from the information, from what we did here, is whether or not this crosses this horizontal asymptote. We didn't do anything to actually figure that out. So it's possible that this could dip below it and stay positive and then still approach 1 underneath it. But it's okay at this point. We'll talk more about that later. Okay. What questions do you have? Anything? Okay, so remember your assignment for this, remember, I don't know if I said it, but your assignment that goes with this, you're not actually having to graph, you're just going to find the pieces like we found. The next time we graph together, then you will have some that you're going to be graphing on your own. Okay.